Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stacks series. Today we are exploring the hidden architecture of causes and effects, inverse problems, and causal inference.
And the material we've got piled up on the table today is, it is nothing short of staggering. We're pulling from advanced geophysics, structural causal models, physics-informed neural networks, and even the group theory of mathematical symmetry.
Yeah.
It spans multiple disciplines, but it really all revolves around one central, monumental challenge that science faces every single day.
Right, and our mission for this exploration is to figure out how science actually reconstructs the invisible. Because if you think about it, how often do we only have access to the aftermath of an event? We're constantly trying to figure out the exact recipe when we only have the finished cake sitting on the counter. Like, how do researchers find the precise underground location and the exact tectonic force of an earthquake just by looking at the ripples that eventually reach the surface? Or if we look at human health, how do epidemiologists isolate the true biological root cause of a disease when the medical data is hopelessly tangled up with thousands of other environmental and social factors?
Yes, messy.
It is. Basically, we're playing detective with the universe, and we're looking at the tools that let us work backward from the clues.
And playing detective requires exceptionally rigorous tools, especially when the universe is, actively trying to obscure the evidence from you. So my goal today is to lay out the complex mathematics and the statistical frameworks that make this backward-looking detective work possible.
Which we need.
Yeah, we're going to look at the rare moments when the math behaves perfectly, and we're going to spend a lot of time on what happens when the math completely and catastrophically falls apart. Because in the real world, outside of a textbook, things rarely go smoothly.
They really don't. Okay, let's unpack this from the very beginning.
Yeah.
We need to start with the foundations.
Right.
Section 1, what we actually think we know about cause and effect.
Right.
Before we can talk about doing things backward, we probably need to define what it means to do things forward. I see these terms, forward problem and inverse problem, all over these papers.
Yeah.
Can you just break down what a forward problem actually looks like in practice?
Sure. A forward problem is basically the direction of natural time and logical physics. It
Right.
goes directly from cause to effect.
Okay.
It's entirely predictive. If you know the governing laws of a particular system and you know the exact initial conditions, you can calculate what the end result will be.
Just like a guaranteed outcome.
Exactly. Let's take classical mechanics. If I know the exact mass of the Earth and I know its exact density distribution from the core all the way to the crust, I can use the laws of gravitation to calculate what the gravitational pull will be at any specific point on the surface.
Right.
I have the cause, the mass and density, and I use the rules to calculate the effect, the gravity you feel standing on a specific mountain.
That feels very safe. It's comforting. It really is like baking a cake. If I go into the kitchen, take out exactly 2 cups of all-purpose flour, 1 cup of granulated sugar, a teaspoon of vanilla extract, and I bake that batter at 350 degrees Fahrenheit for exactly 30 minutes, I know exactly what kind of cake is coming out of the oven.
You know the inputs and the rules.
Right. I know the ingredients, I know the thermal rules of the oven, so I know the effect. That is the forward problem. But the inverse problem is what we are actually here to talk about, and that is where the comfort completely vanishes.
Completely. Because the inverse problem reverses the arrow of logic. It goes from the observed effect back to the unknown cause.
So sticking with that kitchen analogy, an inverse problem is when you walk into a room and there's a slice of a completely unknown cake sitting on a plate.
Yeah.
You have absolutely no idea who baked it. You take a bite, you taste the sweetness, you look at the crumb structure, you feel the moisture level. And from that final finished effect, you have to reverse engineer the exact recipe.
Yes.
You have to tell me if they used 2 cups of flour or 2 1/4. Did they use baking soda or baking powder? Was the oven at 325 degrees or 350? Reconstructing those original parameters from the finished product seems incredibly difficult, maybe even impossible to do with perfect accuracy.
It is incredibly difficult, and that fundamental difficulty was formalized mathematically over a century ago. Back in 1902, the French mathematician Jacques Hadamard was studying partial differential equations,
Okay.
and he realized that not all mathematical problems are created equal when it comes to solving them in the real world. He established 3 specific criteria to define what makes a mathematical problem, quote-unquote, well-posed.
Well-posed meaning it actually works.
Right. If a problem meets these 3 criteria, it behaves nicely. If it fails even one of them, it becomes a nightmare.
I'm looking at these 3 criteria in our notes, and they sound simple enough on paper. Number one, a solution must exist. Number two, the solution must be unique. And number three, the solution must be stable, meaning it depends continuously on the data.
Yeah, those are the three.
But I have a feeling the universe doesn't like to play by these rules. Let's look at that first one. A solution must exist. In the physical world, is that ever really an issue?
In physical inverse problems, existence usually isn't the primary hurdle. I mean, if you are holding a physical piece of cake, a recipe for it obviously exists. Someone baked it.
Right.
If you are standing on the ground measuring a gravitational anomaly, some mass under the ground exists to cause it. The effect is right there in front of you, so the cause, logically, must be real. The trouble begins immediately with Hadamard's second criterion, uniqueness.
Uniqueness. This means there is only one single, solitary answer that could possibly explain the data.
Exactly one.
But wait, if I am tasting that unknown cake, I might think it has white sugar in it. But what if the baker used a specific blend of honey and agave syrup that just happens to perfectly mimic the exact flavor profile and texture of white sugar?
That is the perfect example.
If those two completely different sets of ingredients lead to the exact same tasting cake, doesn't that violate the uniqueness rule?
It absolutely violates the uniqueness criterion. If multiple different causes can produce the exact same observable effect, the inverse problem does not have a unique solution.
So you're stuck.
You're stuck. You cannot mathematically look at the effect and definitively declare, I know exactly what caused this because there are 2, 3, or maybe infinite scenarios that produce identical clues. We will see later how this non-uniqueness creates terrifying scenarios in medical imaging.
Wow.
But as bad as non-uniqueness is, it's Hadamard's third criterion that causes the most widespread devastation in science: stability.
The stability crisis. This brings us to the second part of our foundational section, the nightmare of ill-posed problems. I need you to explain this to me, because looking at the math in these geophysics papers, it seems like the equations just spontaneously self-destruct when they try to go backward. What does it mean for a solution to be stable, and why does reality refuse to be stable?
Well, a problem is mathematically stable if a microscopic infinitesimal change in your starting data only leads to a similarly microscopic infinitesimal change in your final answer.
Okay, so proportional changes.
Right. If you input 1.0001 instead of 1.0000, your calculated answer should only shift by a tiny fraction. But in almost all fascinating inverse problems, whether in seismology, radar detection, or thermal dynamics, this is completely violated. They are what Hadamard called ill-posed.
Why, though? Why does the math explode just because we run it in reverse?
Think about the physics of a forward problem. Imagine a concentrated burst of intense heat injected into the center of a solid metal block. Over time, that heat dissipates. It spreads out, it softens, it warms the entire block evenly.
Okay, makes sense.
Or think about a sharp, violent seismic snap deep in the earth. By the time those energy waves travel miles through the rock to reach the surface, they have smoothed out into rolling vibrations. The mathematical operators that govern these natural forward processes act as intense smoothers. They take sharp, high-frequency, concentrated signals and blur them out over space and time.
I picture that like taking a crisp, high-resolution digital photograph of a person's face and then running it through a heavy blur filter in Photoshop. The sharp edges of the eyes, the individual strands of hair, they all get blended and smoothed out into a hazy gradient.
That is an excellent way to visualize it. Now, if the forward physical process is a massive blur filter, what must the inverse mathematical process do?
The opposite.
Exactly. To reconstruct the original cause, the inverse operator has to act as an incredibly aggressive sharpener. It must mathematically amplify high-frequency details to reverse the smoothing effect and find those sharp original edges.
But here is where it gets really interesting and where the whole thing falls apart. When we collect data in the real world, when we take a picture or measure a tremor or read a thermometer, that data is never, ever mathematically perfect.
Never.
There's always noise. A literal speck of dust on a camera lens. A microscopic gust of wind hitting a seismic sensor. A tiny rounding error in a digital thermometer.
And that tiny speck of noise is the fatal blow. Because the inverse mathematical operator is designed to aggressively amplify high-frequency details, it cannot tell the difference between the actual underlying signal and the microscopic noise.
Oh, no.
So it takes that speck of dust, that tiny whisper of static, and it amplifies it by a factor of thousands or millions. It blows that microscopic error up into a gargantuan mathematical artifact.
It's like using the sharpen tool on that blurry photo, but there is a single, barely visible pixel of white static in the corner. When you crank the sharpening tool all the way up to reverse the blur, that one pixel gets amplified until the entire photograph turns into a blinding, meaningless screen of white noise. The solution explodes.
It becomes complete physical nonsense. The algorithm might confidently tell you that the temperature inside the metal block was negative 10,000 degrees, or that the earthquake was caused by a rock moving at the speed of light.
Just totally absurd.
Completely. The solution is violently unstable. A tiny change in the data, the addition of one speck of noise, completely destroyed the answer. Therefore, nearly every interesting problem in physics is fundamentally ill-posed.
It sounds hopeless. I mean, if our sensors can never be perfect and the math amplifies imperfections to infinity, how has science progressed at all? Humans have been trying to solve inverse problems long before we had supercomputers to complain about noise.
Science progresses because we rarely rely purely on the raw data. We bring outside knowledge into the equation. What's fascinating here is how ancient this practice is. Humans have intuitively understood how to stabilize ill-posed problems for millennia.
That reminds me of the incredible historical anecdote from our stack of sources about Aristotle. We are talking over 2,000 years ago, and Aristotle was trying to figure out the geometric shape of the Earth.
Yes, a classic inverse problem.
He couldn't fly into space to look at the cause directly. All he had was the effect. Specifically, he observed the shadow that the Earth cast on the surface of the moon during a lunar eclipse. He saw that the edge of the shadow was curved.
And from a purely mathematical standpoint, solving an inverse problem in projective geometry using only a single shadow is ill-posed. It violates the uniqueness criterion.
Because other shapes could cast that shadow.
Yes, a spherical Earth casts a curved shadow. But if the Earth were a flat, two-dimensional disk like a drum, and it happened to be angled just perfectly relative to the sun and the moon, it would cast the exact same curved shadow. The raw data of the shadow alone does not uniquely prove a sphere.
But Aristotle didn't get stuck there. He didn't just stare at the math of the shadow and give up. He used what scientists call a priori information, prior knowledge. He stepped outside the boundaries of that specific observation and brought in other physical rules that he believed governed the universe. He observed that all physical matter tends to fall toward a central point of gravity. And he reasoned that if all matter falls toward a center over the long enough time, that matter will naturally clump together into a spherical shape.
By taking the raw, non-unique data of the shadow and combining it with the a priori structural knowledge of how gravity shapes matter, he eliminated the flat disk possibility. He stabilized the inverse problem by constraining the possible answers, and he correctly deduced the spherical shape of the Earth.
Which is brilliant. And that concept, using outside structural knowledge and assumptions to force an impossible problem to behave, is the perfect bridge to the next part of our foundational discussion. We have been talking about physics and gravity and heat, but what happens when the cause and effect we are studying isn't physical matter, but human behavior, biology, or economics? How do we reconstruct the invisible in a messy data set?
This is where we transition from the realm of physical inverse problems into the world of causal inference. When we deal with data medical records, economic indicators, user behavior, we use what are called structural causal models.
Okay.
And to truly understand what a causal model is trying to achieve, we have to look at Judea Pearl and his famous concept, the ladder of causation.
I am so glad we are talking about this. The ladder of causation is one of those frameworks that fundamentally changes how you look at the news or scientific studies or even your own daily decisions. Let's start at the bottom. What is the first rung of the ladder?
The first rung is association. It revolves around the concept of seeing. This is what traditional statistics and early machine learning have spent decades doing. It is the act of passively observing data and looking for patterns and correlations. If you observe variable X, how does that change the probability of observing variable Y?
This is the classic correlation does not equal causation territory. If I stand outside a subway station and observe people, I might notice that on days when a lot of people are carrying umbrellas, a lot of people are also wearing rain boots.
Yes.
The data shows a massive association between umbrellas and boots. But if I steal someone's umbrella, it doesn't cause their boots to vanish. They are just associated because of a hidden third factor, the rain. Association is just drawing lines between things that happen at the same time. It doesn't tell you how the system actually works.
To understand how the system works, you have to move up to the second rung, intervention. This is the realm of doing. You are no longer a passive observer, you are an active experimenter. You want to know what happens if you intentionally reach into the system and change a variable.
So instead of just watching people, I actively hand out umbrellas to random people on a completely sunny day.
Exactly. You intervene, and then you observe whether your intervention caused them to suddenly go buy rain boots. When they don't, you have proven that umbrellas do not cause rain boots.
Huh.
In medicine, this is the randomized controlled trial. What happens if we actively force this group of patients to take a new blood pressure medication and withhold it from this other group? To answer questions on this rung, you need a causal model that understands the directional flow of influence. You are testing the mechanics of this system.
Which brings us to the very top of the ladder, rung number 3. This one always feels a bit like science fiction to me.
Counterfactuals.
Counterfactuals are the pinnacle of human reasoning and the hardest challenge in causal inference. They deal with imagining. This is retrospective reasoning about a specific individual or event that has already happened. You are asking, given what I know happened in reality, what would have happened if I had done things differently?
So if a patient is given a new experimental drug, and unfortunately that patient passes away, the counterfactual question is, if this specific patient with their exact medical history, their exact genetics, in that exact hospital had not been given the drug, would they have survived? That is the crucial distinction. You aren't asking about average outcomes for a population anymore. You are asking about an alternate reality for a single data point. To mathematically calculate a counterfactual, you need an extraordinarily accurate, deeply detailed functional model of the entire data-generating process.
That sounds intense.
It is. You have to be able to mathematically rewind time, alter a single node in your causal graph, and simulate the forward physics of an alternate universe.
So what does this all mean? Why does this matter to you listening right now on your commute or while you make breakfast? It matters because your life is dictated by these concepts. Every time you read a headline that says coffee causes longer life, or every time the Federal Reserve adjusts interest rates expecting to fix inflation, or every time an algorithm decides which news article to show you, they're all trying to climb this ladder.
They are.
They're all attempting to solve a massive inverse problem, trying to tease out the true underlying laws of cause and effect from an ocean of noisy, chaotic data.
And this naturally pushes us into Section 2, the active debates. Where does the science actually disagree right now? Because we have established a rather bleak picture. Physics inverse problems want to violently explode because of tiny specks of noise. Statistical data is inherently messy and full of false associations.
Yeah, that looks bad.
So when an engineer or a data scientist sits down at their computer today, how do they actually force these ill-posed problems to yield a useful answer?
They use a mathematical leash. The technique is called regularization, and the grandfather of this technique is Andrei Tikhonov, a Russian mathematician who developed what is now famously called Tikhonov regularization. Let's unpack how this works, because it's essentially a brilliant hack to stop the math from amplifying noise.
It is a modification of the core optimization problem. Normally, an algorithm tries to find a cause that perfectly 100% matches the observed effect. But as we discussed, demanding perfection forces the algorithm to fit the microscopic noise, which explodes the solution. Regularization says, stop trying to be perfect. Instead of just calculating the match, you add a mathematical penalty term to the equation. You force the algorithm to find a cause that matches the observed data reasonably well, but also satisfies an additional constraint.
I have a visual for this that helps me understand it. Imagine you are walking a dog in a large open park. The raw, noisy observations you've collected from your sensors is the dog. And this dog is erratic.
Highly erratic.
Right. It's pulling wildly in every possible direction, chasing every squirrel, stopping to sniff every single tree. If you just follow the dog, which is the equivalent of solving the unregularized inverse problem, your path through the park is going to be chaotic, jagged, and entirely meaningless. It is completely unstable.
But the dog is reacting to the high-frequency noise in the environment. So what is the leash in this analogy?
The leash is the Tikhonov regularization penalty. You attach the leash, and you serve as the anchor. The dog still pulls toward the data, but the leash pulls back. It constrains the movement. It forces the final path you take through the park to be somewhat smooth and sensible, rather than a frantic zigzag.
That is a highly accurate representation of the math. By adding a penalty, often a penalty against the solution, becoming too jagged or having numbers that grow too massive, you stabilize the operator. The active debate among mathematicians, however, is a question of tension. How tight do you hold the leash?
Right. Because if you give the dog one of those retractable leashes and let it run 50 feet away, the leash is too loose. The dog is still yanking you into the bushes.
Yes.
In mathematical terms, your penalty is too weak and you are still fitting the noise. The algorithm still thinks the static on the lens is an important feature of the image. But what if you wrap the leash tightly around your hand and pull the dog right against your leg?
If the leash is too tight, you over-regularize, you strangle the solution. You force the algorithm to be so smooth and so rigid that it completely ignores the valid data. You blur out the actual truth.
So you miss things.
Exactly. If there was a genuine sharp anomaly in the data, like a real fault line or a real tumor, a leash that is too tight will just mathematically iron it out as if it wasn't there. You miss the discovery.
So how on earth do they decide what the perfect tension is? How do you pick the right mathematical penalty?
There are several philosophies, but one of the most prominent discussed in our sources is the Morozov discrepancy principle. It provides a logical framework for setting the tension. The principle argues that the regularization penalty should be calibrated to exactly match the known noise level of the instruments.
Okay, let's break that down. If I'm using a digital thermometer and I know from the manufacturer that it has an error margin of plus or minus 1%.
Exactly. You know your data is only accurate to within 1%. Therefore, the Morozov principle dictates that you should set your regularization parameter so that the algorithm only tries to match the data down to a 1% difference.
Oh, wow.
Once the calculated cause produces an effect that is within 1% of your observations, the algorithm stops trying to get closer. It actively refuses to match the data perfectly because it knows that the final 1% is nothing but noise.
It's essentially telling the math, good enough is literally better than perfect. But the research stack gets even more nuanced than this. Our sources dive into something called distributed Tikhonov regularization. Because we aren't always just looking for one simple, uniform thing. What happens when the invisible cause you are trying to reconstruct is highly complex and has different types of features?
This raises an important question about the limitations of a single leash. Imagine you are a radio astronomer trying to reconstruct an image of space from raw, noisy frequency data. The image you are trying to build has two very distinct components. First, the deep void of space, which should be mathematically smooth and continuous.
Right.
Second, the stars and galaxies, which are tiny, sharp, highly concentrated points of intense light. Mathematicians call this sparse data.
So if you use one global regularization penalty, one standard leash for the whole image, you're doomed. If you use a leash that promotes smoothness to make the background space look right, you blur the sharp stars into fuzzy smudges.
Oh.
If you use a leash that promotes sharpness for the stars, the background void fills up with noisy, static-like artifacts.
Precisely. Distributed Tikhonov regularization is the solution to this. Why apply the same mathematical penalty to everything? In this framework, you break the unknown cause into distinct components and assign different leases to each one.
It's like walking a pack of dogs. You have a greyhound, which is the sparse data, and a bulldog, which is the smooth data. You wouldn't use the exact same leash tension or harness for both.
Mathematically, scientists apply an L1 norm penalty to the components of the data that they expect to be sparse. The L1 norm mathematically forces most of the values to absolute zero, allowing only a few sharp spikes to exist, perfect for capturing the isolated light of stars.
And for the void.
Simultaneously, they apply an L2 norm penalty to the background components. The L2 norm heavily penalizes sharp jumps and forces the values to transition smoothly, perfect for the dark void. By distributing different types of regularization across the problem, they achieve incredibly nuanced, stabilized reconstructions that a single penalty could never manage.
That level of mathematical engineering is staggering. But let's shift our focus back from the physics of space to the chaos of human society. If we look at causal inference, the active debates aren't just about smoothing out noise. The biggest, most contentious crisis in observational statistics today is the hunt for ghosts. We are talking about the unobserved confounder.
The unobserved confounder is the absolute bane of data science. It is a hidden variable that you have not measured or cannot measure, which secretly influences both the supposed cause and the supposed effect. By doing so, it creates a spurious, completely fake correlation that tricks your algorithm into thinking it has found a causal relationship.
I see this constantly in the news, but let's walk through a classic, rigorous example to see how dangerous this ghost really is. Imagine a massive medical study. Researchers want to know if a brand new, expensive daily supplement improves overall long-term cardiovascular health. They can't do a controlled trial for 20 years, so they look at observational data from 50,000 people.
Okay.
They run the numbers, and they see a massive, undeniable, positive correlation. People who take the supplement have significantly stronger hearts and lower blood pressure.
The naive conclusion, residing on the first rung of Pearl's ladder, is that the supplement causes better heart health. But the researchers have failed to measure an unobserved confounder, socioeconomic status, or SES.
And SES is incredibly tricky. You can't just draw blood and measure someone's SES. It is this massive, complex, invisible web of factors. It includes their bank account, the quality of the public schools they attended, the crime rate in their neighborhood, their access to fresh grocery stores versus fast food, their chronic stress levels from their job. It is a deeply entrenched, holistic state of living.
And here's why SES is the ghost haunting the data. A high socioeconomic status makes a person significantly more likely to have the disposable income necessary to buy this expensive daily supplement. So SES causes the treatment.
Right.
Simultaneously, high SES independently leads to better cardiovascular health because these individuals have lower chronic stress, more time to exercise, and better diets, entirely regardless of whether they take the supplement or not. So SES also causes the effect.
So if the researchers haven't measured SES, their data is hopelessly compromised. The supplement might literally be made of completely inert chalk, might do absolutely nothing biologically, but the data will still show that supplement takers are healthier because the supplement is just a marker for wealth. The entire miracle drug effect is just the hidden influence of privilege.
This is the unobserved confounder crisis. If you can't see the ghost, your causal model is invalid. So how do statisticians try to fight a variable they can't measure? They rely on what are known as proxy variables.
A proxy, like a stand-in. If I can't measure the massive, holistic web of socioeconomic status perfectly, I look for things I can measure that might cast a shadow of it. I can pull a person's zip code, I can look at their tax return for their reported income last year, I can check a box for their highest level of education. These are proxies. They are noisy, imperfect, fragmented reflections of the true hidden confounder.
And the active debate in the literature is how to mathematically use these imperfect proxies without accidentally breaking the model further. Historically, statisticians used linear regression. They would take the proxy, like zip code, and try to draw a straight mathematical line through it to adjust the data. But our sources make it clear that linear models fail catastrophically when the hidden confounder is complex.
Why do they fail?
Because reality isn't a straight line. The true hidden confounder of SES might be a nonlinear combination of continuous data, like a precise salary down to the dollar interacting with categorical data, like whether someone has a master's degree or a bachelor's degree.
That's way too complicated for a straight line.
Exactly. If you try to untangle that complex multidimensional web by just drawing a straight linear adjustment based on a zip code, you leave massive amounts of confounding bias in the data. The ghost is still there.
And just when you think you figured out how to use proxies, the sources introduce a trapdoor that can make your data even worse. It is the specific debate surrounding post-treatment bias. This is where the timeline of events completely scrambles your math.
Post-treatment bias is an insidious logic trap. The fundamental rule of causal inference is this. When you are trying to estimate the effect of a treatment, you absolutely, unequivocally must not control for any variables that were caused by the treatment itself.
If you control for something that happened after the treatment, you accidentally block the very causal pathway you are trying to measure. Let's unpack this with the corporate hiring example from the text because it makes this abstract trap very real. Imagine a large tech company. They decide they want to switch a specific, highly technical job role from being strictly on-site in a cubicle to being fully remote and online. The treatment in this experiment is the announcement of the switch to online work. The company wants to measure the causal effect of this treatment on applicant behavior. Do they get a higher caliber of applicants? Do candidates negotiate differently? Do more people accept the final offer?
To get an accurate causal estimate, the company's data scientists know they need to control for the candidate's underlying preferences. They need to compare apples to apples. How does a candidate who naturally prefers remote work react to the announcement versus a candidate who naturally prefers office work? But a candidate's deep-seated internal preference is an unobserved confounder. You cannot scan their brain to find it.
So the data scientists hunt for proxy variables to guess the candidate's preference. They look at the candidate's behavior during the multi-week interview process. They record the specific questions the candidate asks HR. They analyze the tone of their emails. They look at their initial salary negotiation tactics. They gather all this proxy data to build a profile of the unobserved confounder.
But here is where the trap snaps shut. What if the proxy data you are collecting includes decisions and behaviors the applicant made because they found out the job was moved online?
Oh, right. Because the announcement of remote work happened during the interview process. If a candidate hears they can work from home, maybe they change their negotiation strategy. Maybe they ask for less base salary but demand better home office equipment.
Exactly. That new negotiation strategy is a post-treatment variable. It is a direct effect of the treatment. It happened downstream in time. Now, if your statistical algorithm takes that post-treatment behavior and accidentally scrambles it together with the proxy data you are using to estimate their prior underlying preference,
You've mixed the cause and the effect into the same bucket.
you have corrupted the entire model. If you try to control for a variable that is actually a result of the treatment, the mathematics break down. The research papers in our stack are very explicit about the severity of this. They state mathematically that if your proxies scramble confounders with post-treatment variables, the resulting causal estimation can be, and this is a direct quote, arbitrarily bad.
Arbitrarily bad. That doesn't mean it's just off by a decimal point. It means the error has no bounds. The math could output a result pointing in the completely wrong direction. It could confidently tell the company that switching to remote work makes candidates hate the job, when in reality it makes them love it.
It is terrifying when you realize that medical treatments and economic policies are often evaluated using proxy variables that might be secretly contaminated by post-treatment bias.
Which is the perfect pivot to Section 3, the frontiers. We've laid out the nightmares. We've seen how unstable math and unobserved ghosts threaten our understanding of reality. So what is coming over the horizon? What is the cutting-edge science that might change everything? Unsurprisingly, the answer involves artificial intelligence. But we aren't just talking about throwing data at a standard algorithm. We're looking at the fusion of deep learning with strict, rigorous physical laws.
Machine learning is rapidly taking over the entire field of inverse problems. But traditional neural networks have a massive vulnerability. They are fundamentally black boxes of pattern recognition. If you feed a standard AI millions of data points about a swinging pendulum, it will eventually learn to predict how the pendulum swings. But it does not know why. It does not know that gravity exists or that air resistance slows things down. It just knows the statistical correlation of the numbers.
If the AI doesn't know the laws of physics, it can easily hallucinate. It might suggest a solution to an inverse problem where water spontaneously flows uphill, or heat concentrates itself into a single point instead of dissipating, simply because that math happened to fit the noisy data perfectly. It has no physical common sense.
This vulnerability led to the invention of PNN's physics-informed neural networks. This is a monumental leap forward. A PNN is an AI that does not just look at the raw data, it is mathematically chained to the physical laws of the universe.
How do they actually chain it, though?
They embed partial differential equations, or PDEs, directly into the AI's loss function. The loss function is the metric the AI uses to grade its own performance during training. Normally, an AI is only penalized if its output doesn't match the training data, but a PNN faces a dual penalty. It is penalized for missing the data, and it is severely mathematically penalized if it proposes an intermediate step or a final answer that violates the laws of fluid dynamics or quantum mechanics or thermodynamics.
I picture this like training a wildly creative, highly intelligent dog to run an obstacle course, but the dog is physically tethered to a track that represents reality. The AI can use its massive computational power to explore millions of possible solutions to the inverse problem, but it cannot wander into the realm of physical impossibility. The physics constraint violently pulls it back.
It is incredibly powerful. However, our sources highlight that even standard PNNs have a critical flaw when applied to highly complex inverse problems. It has to do with how the AI perceives time.
Here is where it gets really interesting, because an AI doesn't experience time the way we do, right?
Exactly. When you feed a dataset to a standard PIN, it processes the entire block of information simultaneously. It looks at the state of the physical system at time step 1, time step 2, and time step 3 all at once. It optimizes its parameters globally. What it lacks is an inherent structural respect for temporal causality. It does not instinctively understand that the state of the system at time step 2 is strictly and exclusively caused by what happened at time step 1.
Because it's seeing the end of the movie at the exact same time it sees the beginning, It doesn't care about the chronological flow of plot points.
And because it lacks this directional causality, when a standard PNN tries to run a difficult inverse problem backward, it can get confused by complex dynamics and converges on a solution that is numerically accurate but physically unstable. It loses the thread of how the physical event actually unfolded.
And the frontier solution to this temporal blindness is a new architecture called CIPNNs, causal inverse PNs.
CIPNNs fix the flaw by fundamentally rewriting how the AI learns. They impose strict directional causality constraints into the training loop itself. The algorithm is not allowed to look at the whole movie at once. Instead, the loss function forces the AI to heavily prioritize the earliest time steps first.
It has to prove it understands the beginning before it's allowed to look at the middle.
Precisely. It must accurately reconstruct the initial conditions and the immediate subsequent reactions. Only after the error rate at the earliest time steps drops below a certain threshold is the algorithm allowed to sequentially expand its learning window forward in time. It steps through the data chronologically.
That makes so much sense.
By forcing the neural network to respect the forward arrow of cause and effect as it learns to solve the inverse problem, CIPNNs reconstruct highly chaotic systems like turbulent wave equations or complex parabolic heat sources with vastly improved stability and accuracy. They don't just know the physics, they respect the timeline of reality.
That is a brilliant evolution. But AI isn't just learning to obey the rules of time. It's also redefining how we handle the noise problem. We spent a lot of time earlier talking about Tikhonov regularization, the leash we use to stop math from amplifying noise. The newest frontier replaces that simple mathematical leash with a hyper-intelligent generative AI. Our sources detail a framework called RD-DIFFPO.
RD stands for regularization by denoising. And what is truly fascinating here is the technology powering it. RD-DIFFQ uses diffusion models. For anyone paying attention to tech news, diffusion models are the exact same underlying architecture used by popular AI image generators. The programs where you type in a text prompt and the AI generates a photorealistic image from a cloud of static. The scientists in these geophysics papers are taking that artistic technology and using it to map the interior of the Earth.
Let's contextualize this with the specific application discussed in the sources, full waveform inversion, or FWI. This is one of the most notoriously difficult inverse problems in the world. It is used in seismology. Imagine an energy company searching for deep underground oil reservoirs, or geologists mapping out dangerous hidden fault lines beneath a city. They can't dig a hole 5 miles deep.
No, they can't.
So they bounce massive seismic waves into the ground. They might set off controlled explosives or use giant trucks that vibrate the earth. Those energy waves travel down, hit the different layers of rock, water, and magma, and bounce back up as echoes to sensors on the surface.
The FWI process attempts to take those messy, overlapping echoes and calculate a high-resolution 3D map of the subterranean world. But it is profoundly nonlinear, and it suffers from a catastrophic mathematical trap known as cycle skipping.
Cycle skipping. I need an analogy for this, because the math is dense.
Think of it like trying to perfectly align two identical repeating patterns. Imagine you have two combs with very fine teeth, and you want to lay one exactly on top of the other so the teeth match perfectly. If you are off by just a tiny fraction of an inch, the tooth of the top comb aligns with the gap of the bottom comb. Or worse, it skips over its matching partner and aligns with the next tooth down the line.
And if you lock the combs together shifted like that, the entire structure is completely wrong, even though locally, it feels like the teeth are locked in.
That is cycle skipping in seismology. The computer simulation generates a wave, and it tries to match it to the real echo wave from the Earth. But because the waves are complex and overlapping, the algorithm gets confused. It matches the peak of its simulated wave with the peak of a completely different later wave in the real data. When this happens, the optimization algorithm gets trapped in what we call a local minimum. It looks at the local math and says, great, the peaks match, I solved it.
But because it skipped a cycle, the resulting map it generates is a complete hallucination. It might show a solid layer of granite where there is actually a cavern of loose sand. So how does a generative diffusion model fix this? How does it stop the cone from skipping?
It acts as the ultimate intelligent regularizer. The RBD-Q framework works in two stages. First, long before they even look at the real seismic data, the scientists pre-train the diffusion model. They feed it millions of images of highly realistic, scientifically accurate geological structures.
So the AI spends weeks just staring at textbook examples of how rock layers fold, how tectonic faults shear across each other, and how subterranean salt domes push upward. It learns the visual grammar of geology.
Exactly. It builds a deep internal mathematical representation of what the inside of the Earth should look like. Then comes stage two. They start running the mathematical equations for the inverse problem on the real, noisy seismic data. As the math grinds forward, the noise inherently starts pushing the calculations toward the cycle-skipping trap. The emerging map starts to look messy, unnatural, and filled with mathematical artifacts.
But RadiDiffQ doesn't let it stay messy.
At every step of the calculation, the diffusion model steps in. It acts as a structural prior. It looks at the messy, emerging map and uses its vast, pre-trained knowledge of geology to identify the non-physical artifacts and the cycle-skipping errors. It aggressively denoises them. It mathematically reaches into the equation and pulls the chaotic solution back toward geological reality.
It is literally like having an expert geologist standing over the shoulder of the math algorithm. The algorithm draws a weird, jagged spike, and the AI geologist says, no, rock layers don't bend at a 90-degree angle like that. Smooth it out into a curve. The algorithm draws a fuzzy blur, and the AI says, actually, that looks like the start of a fault line. Let's sharpen that edge.
The results detailed in the sources are breathtaking. They tested this framework on the Marmousi and Overthrust benchmark models. In the geophysics community, these are famously complex, highly detailed synthetic models of the Earth used specifically to torture test new algorithms.
And to make it even harder, the researchers intentionally sabotaged the test. They deleted huge chunks of the seismic trace data and injected heavy synthetic noise.
And RadiDiffQ still reconstructed the deep, complex structures beautifully. Where the traditional physics math failed and got trapped in cycle skipping, the generative AI was able to essentially hallucinate the missing physics, but it did so in a mathematically constrained, physically accurate way. It represents a total paradigm shift in how we handle ill-posed physics.
But AI isn't just fixing physical maps. It is also tackling the causal inference nightmares we discussed in Section 2. Remember, the ghost in the machine, the unobserved confounder like socioeconomic status that ruins medical studies. The frontier for hunting that ghost involves another type of AI architecture, VAEs, or variational autoencoders.
Yes. The specific model discussed in our sources is the CEVE, the causal effect variational autoencoder. To understand how it hunts the ghost, you have to understand what a VAE does. It is a neural network designed to find the hidden essence of data. It has two parts, an encoder and a decoder. You feed it a massive, high-dimensional data set. The encoder physically compresses all that data down into a tiny, dense mathematical bottleneck called the latent space. Then the decoder tries to take that compressed bottleneck and decompress it back into the original data.
If the AI can successfully compress and decompress the data, it means the latent bottleneck must contain the fundamental underlying structural rules of that data. It squeezed out all the noise and kept the core truth.
Exactly. The CVA uses this compression architecture to learn the joint probability distribution of everything we observed in the medical trial. It looks at the treatment, the supplement, the outcome, heart health, and all the noisy proxy variables we have. Zip code, tax returns, education level. It feeds all of this into the neural network.
So instead of a human statistician trying to draw a clumsy, straight linear line through a zip code, the AI is looking at the entire web of proxies simultaneously. And through the magic of its high-dimensional compression, it mathematically extracts a representation of the true, hidden confounder from the noise. It builds a mathematical proxy of the ghost itself.
It manages to isolate the hidden structure of socioeconomic status in the latent space, and then uses that clean, extracted structure to accurately calculate the true causal effect of medicine. It strips away the spurious correlation.
But what about that trapdoor we talked about? Post-treatment bias.
Yeah.
What if the proxy data you feed into the AI is contaminated with variables that happened after the treatment? Does the AI just scramble it all together and give you an arbitrarily bad answer?
That is the exact problem that led to the creation of the newer CVAE, the confounder identifiable VAE. The CVAE is explicitly designed to recognize and mathematically sever post-treatment variables so they don't corrupt the confounder. It doesn't just extract a generic blob of hidden variables in its latent space. It subjects those variables to rigorous mathematical interrogation using conditional independence tests.
Okay, stop right there. How on earth does an AI run an independence test on variables that are literally hidden inside a compressed, latent space? It sounds like trying to weigh a shadow.
It is a brilliant piece of causal mathematics. Inside the latent space, the sieve isolates the extracted hidden variables into pairs. Then it checks how closely correlated those two variables are to each other in two different scenarios before it factors in the treatment variable and after it factors in the treatment variable. This is called conditioning on the treatment.
And why does that comparison reveal the truth?
Because of the strict graphical rules of causal models, if two hidden variables are true confounders, meaning they sit upstream and cause the treatment, their statistical correlation will actually increase when you mathematically condition on the treatment. It's a phenomenon called collider bias. However, if one or both of those hidden variables are post-treatment variables, meaning they sit downstream and are caused by the treatment, their correlation will decrease when you condition on the treatment.
That is mind-blowing. The AI is literally watching how the hidden variables react to the presence of the treatment. If they behave one way, it knows they are true prior confounders. If they behave the other way, it catches them as post-treatment imposters.
Precisely. By running these complex conditional independence tests inside the neural network during training, the sieve identifies the imposters, severs them from the causal calculation, and only uses the true prior confounders to estimate the effect of the medicine. It completely solves the arbitrarily bad bias problem.
It is untangling the world's most complicated knot of headphones, but doing it entirely inside a high-dimensional mathematical latent space. Now, before we leave the frontiers, there is one more concept buried in the physics papers that absolutely stopped me in my tracks. It is less about a specific AI architecture and more about the fundamental limits of the universe. It is the concept of group theory and mathematical symmetry.
This is where advanced mathematics borders on deep philosophy. In the era of big data, we have developed this hubris. We tend to believe that if we just build a big enough neural network and if we feed it enough data, we can solve any inverse problem. We believe we can eventually reconstruct any hidden cause. But the mathematics of group theory prove that this is definitively false.
So the universe literally puts up a wall. How does symmetry create a wall?
Let's visualize a physical example detailed in the research. Imagine you are studying fluid dynamics. You have a volume of water, and hidden deep within the water are complex, swirling currents. You can't see the currents directly. But suspended in the water are tiny particles, and you can observe their orientational motion. You can see how they tumble and spin as they are pushed by the fluid. You want to use an AI to solve the inverse problem, watch the tumbling particles, the effect, and reconstruct the exact local velocity gradient tensor of the fluid, the hidden cause.
Okay, I am observing the visible tumbling to reverse engineer the invisible currents pushing them.
Right. But this physical system possesses a specific mathematical property, symmetry. Specifically, it has rotational symmetry in three-dimensional space, which mathematicians classify as the SO3 group.
I need you to break down SO3 for me. What does that actually mean in the real world?
SO3 is the special orthogonal group in 3 dimensions. In physical terms, it means the laws governing how those particles tumble in the fluid are identical regardless of how you rotate your point of view. Think of a perfectly smooth, featureless basketball floating in space. If you close your eyes and I rotate the basketball 45 degrees and you open your eyes, you cannot tell that it moved. Its physical laws and appearance are rotationally invariant. The fluid system has this exact same rotational symmetry.
Okay, so the physics don't care about the angle of observation. Why does that stop the AI?
Because if the physical system possesses SO3 symmetry, the mathematical function that the AI learns, the mapping that goes from the observation back to the cause, must act as a group homomorphism.
Group homomorphism. Let's unpack that without the math jargon.
A homomorphism is a structural preservation. It means that whatever complex algebraic transformations the neural network is doing inside its hidden layers, those transformations must perfectly obey and preserve the SO3 rotational rules of the physical universe. The AI cannot invent a mapping that breaks the symmetry. It is mathematically locked into the algebraic structure of the SO3 group.
And what happens when the AI is locked into that structure?
Group representation theory takes over. Because the AI must obey the homomorphism, the mathematics dictate that only a very specific, limited subspace of the cause can ever be reconstructed. The algebraic rules literally dictate that certain components of the fluid current will never translate into the tumbling motion in a way that can be uniquely mathematically separated.
So the symmetry of the universe proves that there are hard, immutable limits to what any algorithm can ever learn. Certain parts of the cause are fundamentally permanently invisible. No matter how much data you have, no matter how powerful the AI becomes, the geometry of reality prevents that information from ever reaching the effect in a reconstructible way.
Exactly. It is a profound realization. Group theory governs the absolute mathematical limits of identifiability. It humbles us. It proves that AI isn't magic. It is forever bound by the fundamental symmetrical structures of reality.
Which perfectly transitions us into the final section of our exploration today, implications. Section 4. We have spent an hour deep in the trenches of partial differential equations, neural networks, and causal statistics. But what does this mean for society, for ethics, for economics, for how we live our lives? Let's start with a concept that feels like it belongs in a sci-fi thriller, but is a very real danger in medical imaging: the illusion of reality and the terrifying concept of non-uniqueness.
We established right at the beginning that if an inverse problem violates Hadamard's second criterion, uniqueness, it means multiple distinct different realities can produce the exact same observational data. In a math textbook, that is an interesting puzzle. In a hospital, it is a matter of life and death.
The sources focus specifically on techniques like diffuse optical tomography, DOT, and electrical impedance tomography, EIT. These are advanced medical scans. A doctor places electrodes or light sensors around a patient's body. They pass harmless light photons or mild electrical currents through the tissue, and they measure what comes out the other side. By analyzing how the light or electricity was scattered and absorbed, they solve an inverse problem to reconstruct a 3D map of the inside of the body, searching for anomalies like a tumor.
The physics governing how light and electricity travel through tissue are dictated by elliptic partial differential equations. And the mathematics of these equations hold a dark secret. If the biological material inside the body has what are called anisotropic coefficients, you are guaranteed to suffer from severe non-uniqueness.
Anisotropic coefficients. Let's ground that term. What does it mean for tissue to be anisotropic?
It means the physical properties of the material are not the same in every direction. Think of a piece of raw wood. If you try to split the wood with an axe along the grain, it splits easily. If you try to chop across the grain, it is incredibly difficult. The physical resistance changes depending on the direction. Human tissue, like muscle fibers or nerve bundles, is often anisotropic. It conducts electricity or light differently depending on the angle the energy hits it.
And because the tissue is anisotropic, the math of the inverse problem breaks down. It means a completely healthy arrangement of muscle and tissue could mathematically produce the exact same surface measurements as an arrangement of tissue that happens to contain a massive, dangerous tumor.
Yes, and mathematicians have taken this to its logical, terrifying extreme. This leads to the theoretical concept of cloaking. It is mathematically possible to design a specific arrangement of anisotropic materials, a physical shield that surrounds an object or an anomaly and completely hides it from the inverse problem. The shield bends the incoming light or electrical current smoothly around the hidden object and sends it out the other side on the exact same trajectory it would have had if it had just traveled through empty space.
So the boundary measurements read by the sensors on the surface of the skin are identical to empty, healthy space. The tumor is mathematically cloaked. We know this technology is actively being researched for military applications, like designing materials that cloak aircraft from radar. But in medicine, it raises a profoundly unsettling question. If the absolute laws of mathematics dictate that two entirely different biological realities can produce identical scans, how do we ever trust a medical diagnosis based on an inverse problem?
It means we can never rely on a single isolated inverse problem. We have to break the mathematical symmetry of the non-uniqueness. Doctors must combine EIT or DOT with entirely different modalities, like an MRI or an ultrasound, which rely on different physical laws and different inverse math. We also rely heavily on prior structural assumptions about human anatomy to regularize the answers. But it is a stark reminder that a medical scan is not a photograph of reality. It is a highly constructed, mathematically fragile guess.
And speaking of trusting medical tools, this brings up another massive implication: the ethical danger of the black box. We talked extensively about how incredibly powerful neural networks like the CVI at finding causal effects and hunting down hidden confounders. But should we let them make health policy decisions?
This is one of the most hotly debated topics in AI ethics. Let's say a massive hospital network trains a deep causal AI to analyze patient data. The AI looks at millions of records and concludes with 99% accuracy that a certain expensive surgery should be denied to a specific demographic of patients because the causal outcome is poor.
From a purely mathematical standpoint, the AI might be completely correct. It might have successfully untangled the proxies and the post-treatment variables. But it is a black box. It has billions of internal parameters. A human doctor cannot open the neural network and read why it made that decision.
And in healthcare, economics, and criminal justice, predictive accuracy is not enough. We require transparency. We require accountability. If you are going to deny a patient a surgery or deny a citizen a loan based on a causal model, you have to be able to explain the logic to them.
Which is why the frontiers of causal AI are pushing towards something called TRAMDAGs.
TRAMDAGs stand for transformation models with directed acyclic graphs. They belong to a new class of interpretable neural causal models. The goal here is a compromise. We want to leverage the immense nonlinear pattern-matching power of deep neural networks, but we want to violently force them to maintain a transparent, human-readable structure.
So instead of a black box, it's a glass box.
Exactly. The core of a TRAMDAG is the directed acyclic graph. This is a visual map of nodes and arrows showing exactly what causes what. The neural network is still doing the heavy mathematical lifting to calculate the exact strength of the relationships, but the architecture of the network is constrained to directly mirror the visual graph.
So a doctor or a policymaker can look at the output of the TRAMDAG and see the visual map. They can say, I see exactly what happened here. The AI is suggesting we deny the surgery because it found a strong causal link between the patient's age, their specific blood pressure medication, and surgical failure.
It allows human experts to verify the biological or economic logic of the machine before making life-altering decisions. It bridges the critical gap between the alien intelligence of deep learning and the interpretability required by human ethics.
That transparency is crucial for the experts. But what about for the rest of us? Let's bring this all the way down to the listener. What does all this mean for valid inference in our everyday high-dimensional world? Every single day, you open your phone and you are bombarded by headlines claiming that a new study has proven a causal link between two things. Eating chocolate causes weight loss. Scrolling social media causes anxiety. How do you know if the studies you are reading are actually valid?
It is becoming increasingly difficult for the average person because the studies are using larger data sets with more complex variables than ever before, but statisticians are fighting back to ensure validity. They are developing tools like high-dimensional semi-parametric inference.
I love the example used in the text for this because it is something everyone can immediately grasp. Consider a massive observational study investigating the effect of smoking during pregnancy on the birth weight of the child. You obviously cannot ethically run a randomized controlled trial for this. You cannot force a group of pregnant women to smoke.
Therefore, you are forced to rely entirely on observational data. And the moment you rely on observational data, the ghost enters the room. You have to worry about unmeasured confounders, perhaps underlying genetic factors or hidden stress levels, or unreported dietary habits are confounding the data, making smoking look worse, or perhaps better than it actually is.
In the past, researchers would just gather their proxy variables, run the linear math, publish the headline, and just cross their fingers and hope their proxies were good enough to catch the ghost. But today, using advanced inference, they can do something remarkable. They can calculate and publish what is called a causal ignorance region.
A causal ignorance region is a mathematically proven boundary of vulnerability. Modern researchers don't just hand you a single confident estimate of the causal effect. They use complex sensitivity analysis to mathematically prove exactly how much unmeasured confounding would need to exist in the real world to invalidate their study's conclusions.
I find this so empowering. They are showing their work, and they are openly displaying their mathematical vulnerability. The study can publish a result and say, our data shows that smoking reduces birth weight by X amount. Now, we admit there might be unobserved confounders we missed. However, we have calculated the ignorance region, and for our conclusion to be completely false, there would have to be an invisible, unmeasured confounder out there that has a massive 40% independent impact on both a mother's smoking habits and the baby's birth weight.
And this is where human expertise steps back in. Medical doctors and biologists can look at that ignorance region and reason about it. They can say, based on a century of biological knowledge, there is no realistic, unmeasured genetic or environmental factor that has a massive 40% swing on both those variables simultaneously. Therefore, the unmeasured confounder required to break the math does not exist in reality. We can trust the study.
We live in an era of big data, where almost every single piece of information you consume is the result of an inverse problem. From the supercomputers calculating tomorrow's weather forecast, to the AI diagnosing diseases in a hospital, to the economists trying to understand inflation. When you understand the architecture we discussed today, When you understand that these problems are naturally unstable, that they want to amplify noise, that they are plagued by unobserved ghosts, and that they desperately require heavily structured assumptions like regularization, physical laws, and causal graphs to function, it fundamentally upgrades how you process reality. It makes you an incredibly discerning consumer of science and news. Next time you see a bold headline, you won't just accept it. You'll ask, what was their prior assumption? Did they use a tight enough leash? Did they account for the unobserved confounder?
It shifts your perspective from being a passive consumer of facts to an active interrogator of the methods.
It changes everything. And actually, that leads me to a final, slightly provocative thought for you to take away from our exploration today. We have spent all this time talking about inverse problems as highly complex mathematical tools used by scientists in labs with supercomputers. But the truth is, you are solving an ill-posed inverse problem right now. Human visual perception, the very way you are seeing the room around you at this exact moment, is itself a massive, unstable inverse problem.
That is a profound realization. If we break down the physics of vision, the forward problem is strictly mechanical.
Right. Three-dimensional light bounces off the physical objects in your room. That light passes through the lens of your eye, and it hits the retina at the back of your eyeball. The retina is a flat, two-dimensional surface. That is the forward physics. A vibrant 3D reality is mathematically compressed and flattened into a noisy 2D data signal of electrical impulses.
But you don't experience the world as a flat 2D spreadsheet of light. Your brain has to solve the inverse problem in real time. It receives those flat, noisy 2D electrical signals, and from that limited effect, it has to reconstruct the cause. It has to instantly mathematically build the vibrant, deep 3D world in your conscious mind.
And because it is going from 2D back up to 3D, it violently violates Hadamard's uniqueness criterion. Countless different 3D shapes and lighting arrangements could theoretically cast the exact same flat 2D pattern on your retina. The visual data you receive is fundamentally non-unique and ill-posed.
So how does your brain solve this impossible problem millions of times a second without exploding into visual static? It relies on the ultimate, lifelong regularizer, your past experiences. Your brain applies a massive structural prior based on everything you have ever seen, touched, and interacted with since the moment you were born.
Your brain assumes that light naturally comes from above because of the sun. It assumes that most rooms have square corners. It assumes that human faces have a specific geometry. It heavily mathematically penalizes any interpretation of the raw visual data that doesn't fit its prior model of reality. It forces the image to make sense.
Which means your vision is not a perfect, objective window into the physical universe. It is a stabilized construction.
So the question to mull over as you go about your day is this: are you ever truly seeing the objective physical world, or are you just intimately experiencing your brain's most highly stabilized, heavily regularized guess? Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.